Good morning to all of you. Today's lecture is I'm continuing with the n queens problem. Yesterday I finished with the placing the queen in the row. Let me once again repeat the kind of problem it is. Let's say there is an 8x8 chessboard. So you have to place, if it is an 8x8 chessboard, that means you will have to place 8 queens, right? When you place 8 queens, each queen will be placed at one of the rows. Now the constraint is that the queen will attack the other queen if you the queen will attack the other queen column wise or diagonal wise, and we came about with these conditions also, right? So if these conditions are true, so that means the queen is attacking, right? So we'll let me once again explain this place algorithm, which I explained yesterday also, and then I will forward the discussion for backtracking. Now this is the place algorithm. This R2C2 is the row, right, and the column for the next queen, and in my case the next queen is, let's say, Q2. Okay, now it has to when you are trying to place a queen in one of the rows, it will check for all the previous rows if any of the queen in the previous rows is not attacking the present queen, right? So that's why this for loop is there. This is for the previous queen from ranging from R1 to R2 minus 1. All the previous queens which we have already placed in the rows, and we are now trying to place R2. So we will place the queen, right? Now we will this will be the column value for the queen, and if C1 is equal to C2, that means the previous queen is attacking the next queen column wise, or R1 minus R2, C1 absolute value of R1 minus R2 equal to absolute value of C1 minus C2, and this condition was for the diagonal attack. So if this is true, right, so it will return false. That means the position at which we are trying to place the queen is not a suitable position, right? And if these conditions are not true, right, then it will if these conditions are met, then that is not a suitable position for the queen, and if these conditions are not met, so that means that's the place for queen to be placed. So this is the place algorithm in which we can check whether a given position is safe place for the queen or not. The excuse me, the algorithm returns false if the place is not a safe place, that is the queen in question cannot be placed at that position, otherwise it returns true. That means that's a safe place for the queen to be placed. Using this place algorithm, we can now design a backtracking algorithm to place n queens in an n cross n chessboard. Let's see how the algorithm goes. Now this is the backtracking algorithm. Algorithm is n queens, right? This is the row value. The parameter to be passed in this algorithm is the row value. I have given the comments also. We are given a row value at which place we want to place the queen. Now we are checking for all the possible columns because we are trying to place a queen in a row, and we are trying out all the possible positions in the row. So that means we are trying to look for all the columns. If it is an n queens algorithm, we will have to check column 1, column 2 in that same row. Column 1, column 2, column 3, right? Column 4, all the n columns we will have to check whether that's a suitable place or not. And the next point is if place, right? So that's the place algorithm which we discussed previously. So for the row and column, if we find a place which is feasible for the queen, then we place the queen in that row and that column. So place algorithm will tell us whether the position that we are looking for in that particular row is suitable or not. So if we find a suitable place, we will place the queen there. So QR is equal to C, that's the placing of the queen at that particular row. and we will check if r is equal to n. So that means if it is the last, if r is equal to n, then we will display the queens. That means all the queens are placed. All right. Otherwise, if else n queens are plus 1. If that is not a suitable, if r is not equal to n, that means we have not placed all the queens. So that means we will and then we will call the, so let's see, once we place all the queens, we display the queens, that's fine. Now try to place, otherwise we try to place the queen in next row. Um, if that means the suitable place is not there. If the suitable place is not found for the queen to be placed, then it enters into the else part and it makes a recursive call to the n queens algorithm with the next row, right? Uh, Otherwise, we try to place the queen in next row. Okay, so let's look at this example and let's try to understand this algorithm, whatever is written with the help of this example. The first value passed on is row 1. This is the example I have taken this for the 4 queen problem. So n queens 1, that means first call is made to this algorithm with r equal to 1. So we will have to look for all the columns, but what the place algorithm will do, it will look into the first row. We are trying to place the queen in the first row because r value is equal to 1 and we are checking for all the columns. But if for placing the first queen, first line of the code says the check for all columns from 1 to 4. Second line is when r is equal to 1, c is equal to 1. That's a suitable place, actually place the queen there. Fourth line says that r is not equal to n. That means 1 is not equal to 4. All right. Then else it enters into the else part and it again makes a recursive call to the n queens algorithm with a value of r to be 2. Now value of r is 2 and again it will enter into the for loop. It will check for all the columns. R is equal to 2, C is equal to 1, invalidate position because the place algorithm will not give a suitable, will not call it a suitable position. So it is an invalidated by place algorithm. R2, because we have placed the first queen here. Now we are checking for the second queen. For this R2 is equal to R is equal to 2 and C is equal to 1, not possible. R is equal to 2, C equal to 2, not possible because diagonally the first queen will attack. R is equal to 2, C equal to 3. R is equal to 2 and C equal to 3. So this is a suitable position for the queen to be placed. So we will place the queen at Q2. As I told you yesterday also, that this index will give me the row and the value will give me the column. So we place the queen here at this position. But please remember, it is into a for loop. The for loop has to run for 4 times. All right, but it has run only for 3 times. This is a very important point because this is the point which will be used in the backtracking. Let's see how. So my first queen is placed at this position, second queen is placed at this position. Now let's check for, it makes the next call. So r is not equal to n. I have placed the queen. R is not equal to n. It makes the another recursive call with the value passed is r equal to 3. So when r equal to 3, look at this position. Not validated, not validated, not validated, not validated. No position. So you are not able to place your queen number 3 in row 3 because the place algorithm will not validate any of the positions. All right. So this is the stack I am showing. First time it has called n queens 1 with a value of r equal to 1. This is the second call, n equal to n queens for r equal to 2. This is the third call. So no position is validated. So again, we have to use the backtracking algorithm. Let's see how the backtracking algorithm is used. Now, it does not go into if block for all values. Please remember that So once we are n queens 3 function, so what we are trying to do is that in the n queens 3 call, what is happening? We are not able to place the queen. So this function will be popped out. This recursive call is complete. It enters into n queens 2. And as I told you, for this for loop, only 3 times this for loop has run with values of c equal to 1, 2, and 3. The value of c equal to 4 is still left. Now, n queens 2, we will try to alter the position of queen 2 because we have to use the backtracking algorithm. Queen 3 did not find any position, so we backtrack, we reach to queen 2. And in the queen 2 recursive function, we know that the for loop only ran for 3 times. For c equal to 4, this did not run actually. For c equal to 4 and r equal to 2, this is I'm talking for this call n queens 2 when the algorithm has backtracked. So for c equal to 4 and r equal to 2, this is a valid place, and r is not equal to n, then it calls n queens 3 again. So let me explain the algorithm, the major parts of the algorithm. So this loop, this will continue running for all the n queens. I have taken the example of n equal to 4, but this loop, this algorithm will run for n queens. Now let me once again highlight the important points for this algorithm. This is an n queens algorithm, which is a backtracking algorithm. The value, the parameter to be passed is the row value. To start with, I have taken this example of n equal to 4, where 4 queens are to be placed in a 4 cross 4 chessboard. All right. I will, because I have to find a suitable position for the queen. So I will run my for loop for finding the column position from 1 to n. I will use the place algorithm. Now my r equal to start with, for the first call n queens 1, my r value equal to 1, c value will vary from 1 to 4. So it finds the first position, it places the first queen there. So q of 1 equal to 1, right? So that means the queen is placed at 1, 1 coordinate. Now if r is equal to n, no, r is not equal to n. So n queens is again called with r equal to 2. So it goes, n queens is called with r equal to 2. Again the for loop will run for c equal to 1 to 4, right? C equal to 1, r equal to 2, not possible. R equal to 2, C equal to 2, not possible. R equal to 2, C equal to 3, possible. So places the queen 2 at this position. But important point, again and again I'm trying to say, this for loop has to run 4 times. But we have already placed the queen at this position with the third running of the loop. Now I will look for, so I place the queen at Q2 equal to 3. So if R is not equal to, no, R is not equal to n, then n queens again makes a call with R equal to 3. R equal to 3, we will not be able to find any position in row 3. So that's a dead end. It will backtrack. That means the n queens algorithm, n queens 3 algorithm, the n queens 3 call will be popped out from the stack, and n queens 2 will be executed, the remaining portion of n queens 2. And we saw that for loop ran for 3 times, 4th was remaining. So that's what I'm trying to show here, c equal to 4, and that's how queen 2 will change its position from this place to this place in backtracking. And this procedure repeats for all the placings, and this is how the backtracking algorithm works. All right. The place algorithm is to find a place during the forward move. This algorithm n queens is an algorithm to find a place and to adjust the positions of the queens during the backtrack. I hope the backtracking algorithm is clear for the n queens problem. All right. Now that finishes the n queens algorithm. If any problem will be there, I have only taken the example up till here, but rest of the examples will be for even n queen. I explained the problem with 4 cross 4. Even for n cross n, the same procedure or same steps will repeat, and the queens will be backtracked and I mean, the algorithm will backtrack. Queens will be, a position of the queens will be adjusted so that they do not attack each other. All right. Now, today I will also discuss one more algorithm. Okay. Wait. One more algorithm. Oh, sorry. I will have to actually change the file because that's a different file. I have opened a different file. Actually, let me open the file for Hamiltonian cycles. Okay. Let me open the file for Hamiltonian cycles. All right, wait. So today also I will discuss one more algorithm, which is also an example of backtracking Hamiltonian cycles. Now, what is the Hamiltonian cycle in the graph? Now, if a graph is given, start from one vertex. Let's say I'm taking this example 1, 2, 3 with the graph has 6 vertices and some edges. So you start from a starting vertex. You fix any vertex, right? Either 1, 2, 3, 4, 5, 6. But let's say I fix 1. Start from a vertex. Visit all the vertices in the graph. Visit all the vertices in the graph and and reach to the same vertex. All right. So if I start from 1, I go to 2, 3, 4, 5, 6 and come back to 1. Or I go to 1, 2, 5, 6, 3, 4. I mean, I can go with any way. Now, if I am able to reach with the edges given, if I am able to reach at the starting position, so that is called a Hamiltonian cycle. This problem looks like a traveling salesman problem, a traveling salesperson problem, but looks like TSP, but TSP is a minimization problem. Minimization problem means we have to find the minimum cost tour of all the starting from one vertex, we have to find the minimum cost tour of to all the vertices, minimum cost. So but in Hamiltonian cycles, there is no point of minimization of the cost. How many Hamiltonian cycles are there? We have to find all the Hamiltonian cycles. For example, in this graph, one cycle is 1, 2, I have shown it here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and again back to 1. So this is a cycle, this is Hamiltonian cycle. Another can be 1, 2, 6, 5, 4, 3, and then 1. This is another cycle, this is again a Hamiltonian cycle. So one graph can have more than one Hamiltonian cycles. Once you are asked with this kind of problem that you have to look for the Hamiltonian cycles in a graph, so that means you will have to find all the Hamiltonian cycles. But please remember, if the Hamiltonian cycle is like this, 1, 2, 3, 4, 5, 6. So this is the Hamiltonian cycle, but this is not Hamiltonian cycle. The same cycle is there, but if I start from 2, 3, 4, 5, 6, 1, and 2. So that's what I have shown. But 2, 3, 4, 5, 6, 1, 2, this is same as the first cycle. This is a kind of duplicate cycle. All right. So this cycle also remains the same as this first cycle. So this is not another one. We have not to consider this type of cycle in the number of cycles. All right. So we need to check if there is, what is the problem? The problem at hand is we need to check if there is a Hamiltonian cycle possible in the graph. And if there is, then how many Hamiltonian cycles are there? And what are the different Hamiltonian cycles mean what is the root of the cycles? And how many are there? All right. So let's try to understand. Now, look at this. One more example is there 1, 2, 3, 4, 5. If it is a Hamiltonian cycle, no, it's not Hamiltonian. No Hamiltonian cycle is possible because if I go from 1, 2, 4, 3, 5, so I have to come back to 3. That means I cannot complete a cycle by visiting all the vertices only once. All right. So this is not a, this graph does not have any Hamiltonian cycle. This type of vertex, which is the, where you, this is junction of the graph basically, this is also known as the articulation point. So whenever there is an articulation point in the graph, so it does not have any Hamiltonian cycle. Now we will use the backtracking technique to find out how many Hamiltonian cycles are there in the graph. I have taken this example 1, 2, 3. This is the example that I have taken for finding out the Hamiltonian cycles in the graph using backtracking. And this is the adjacency matrix, cost adjacency matrix of this graph. All right. Now I take one array. This is how the algorithm works. I take one array, right, for finding the Hamiltonian cycle. Now I will have to fix the starting vertex. This array, the position of the arrays is corresponding to the vertex number. I will have to fix the starting vertex, because if I do not fix the starting vertex, it will give me duplicate cycles also. So I have to fix the starting vertex so that I have to reach at this point. So once the starting vertex is fixed, I will not be able to get any duplicate cycles. We don't want duplicate Hamiltonian cycles, so we fix the starting vertex. So that means the starting vertex we fix x of 1 is 1. So we fix this starting vertex. So that means my starting vertex is 1 only. What should be the second vertex to find out the Hamiltonian cycle? Now the second vertex is that, look at the second position. Actually, Hamiltonian cycle is basically the depth first search, right? We will see how this works. Now come to this position, change the values. 0 means you have to change the values. First you change it to 1, but 1 already exists. So it will, the algorithm will try to put 1, but it is already there at x1. So it 1 cannot be placed here. Now it puts 2, right? So when it puts 2, it will also check if edge is there from 1 to 2 or not, right, in the graph. So we will have to check from there, from 1 to 2, if there is an edge. Yes, there is an edge. So I can place 2 here. I can come back, I come to the next position. This is 0, right? I change the value to 1. 1 is not possible, already there. 2 is already there. 3 is possible. So that's how the graph is also moving forward. 1, 2, I put the value 3 here, right? This entry is valid. So I will have to check there. I will have to check an edge from the previous value. So I will have to check whether there is an edge from 2 to 3. This is row number 2 to 3. Yes, there is an edge. So 3, this position is valid. So 1, 2, 3. This is fine. This position I get 1, 2, 3. Now I come back to the next position. So again I will have to change, check for all the values 1, 2, 3, 4. So 4 value is not there already in the array, but I will have to check whether there is an edge from 3 to 4. So in the adjacency matrix, edge from 3 to 4. Yes, there is an edge, so it's a valid entry. So 1, 2, 3, 4. So the next vertex in this search is 4. I go to the next value. I put 1, 2, 3, 4. Not possible. I put 5. I put 5. That's a valid entry. But I will have to check also whether there is an edge from 4 to 5. So whether there is an edge from 4 to 5. Yes, there is an edge. So it is a valid entry. So it is 5. Now I will have, so this reaches to the last vertex, but in the end, I will have to again check whether there is an edge from 5 to 1. So whether there is an edge from 5 to 1, yes, there is an edge from 5 to 1. So this way, the algorithm will give me the first Hamiltonian cycle. All right. Here, yes, please. Ask if some question is there.
Sir, your video is paused, sir. We can see the same slide from the last time.
From the?
Sir, from the last time, we're seeing the same slide. It does not do for all values.
Pardon?
So we can see the same slide again and again. Sir, the slide isn't being moved forward.
Sir, your screen has frozen to a previous slide.
Okay, so that means you're not able to see this.
No, sir.
No, sir.
Wait, what I will do is, because I changed the file, I think I will again start the meeting. All right, and I will use the same ID. I will again start the meeting. Then probably that file will come. Wait
Okay,
for
sir.
2-3 minutes.